హలో. హలో.
మేడం
వినిపిస్తాందా అనిల్?
వినిపిస్తుంది మేడం.
అదేలే చెక్ చేస్తాను. ఆయన జాయిన్ అవుతున్నారట.
ఆయన పాకిస్తాన్ అయిన కదా మేడం?
పాకిస్తాన్ ఉల్ హక్ అని ఉంటుంది.
ఓకే మేడం.
ఇంకా రాలే, వస్తానన్నాడు 2కి అట్లా.
అదే రిజ్వాన్
ఉల్ హక్ ఆయనే.
ఓకే మేడం.
ఓకే. హలో హలో
మేడం చెప్పండి మేడం.
మ్యామ్ ఇచ్చారమ్మా రిజ్వాన్ ఉల్ హక్ సార్ జాయిన్ అయ్యాను అన్నారు.
నేమ్ ఏం పెట్టారో మేడం?
నేమా అదే చూస్తున్నాను నేను కూడా. ఆయన పేరు పైన వచ్చుకుంటారు. జస్ట్ అడుగుతాను. జాయిన్
మేడం మీ స్క్రీన్ కొంచెం డౌన్ చేయండి మేడం. ఎందుకన్నా? ఓకే మేడం.
RIZ అంటానా? RIZ అని ఉంటున్నానా?
రాలేదు మేడం.
రాలేదు కదా?
రాలేదు మేడం.
RIZ అని ఉంటున్నాను. నాట్ విజిబుల్. వచ్చింది చూడండి, RIZ వచ్చింది చూడు.
ఎస్ మేడం. ఎస్ మేడం ఇచ్చాను మేడం.
ఇచ్చాను. ఓకే
ఓకే మేడం మీకు హోస్ట్ ఇచ్చేసి నేను లెఫ్ట్ అవుతాను మేడం.
ఓకేనన్నా. ఓకే సార్, గుడ్ ఆఫ్టర్నూన్ సార్. రిజ్వాన్ సార్.
Good afternoon, madam. How are you doing?
అన్న సౌండ్ ఒకసారి చూడు అనిల్.
మేడం అతను సౌండ్ వాల్యూమ్ లో ఉన్నట్టు మేడం. అతను
Sir, can you increase your volume, sir?
Let me try. Can you hear me now?
Yeah, it's okay, sir. Now it's audible, sir.
Okay. So, will you please
Sir, if
suggest
you want to check here at the bottom, you have the share option, sir.
Okay.
Bottom of the screen.
Okay.
Mute, stop video, share.
Okay.
So here from this share, you can share your screen, sir. Yeah, now it's okay, sir. Yeah, it's visible, sir. Now it's visible. Your screen is.
Okay.
So we'll start by 2:30 sharp, sir. Just 5 minutes, sir. You can wait for
No problem.
5 minutes. ఏం చేయగలుగుతాం కాదు అసలు రాలేదు
problem. Yeah. Yeah. If you have a class, do you have a class? Okay, no problem.
The session will start in couple of minutes.
Okay, ma'am.
Yes, sir. Good afternoon to one and all. I welcome all the participants to the third day of 1 week virtual international lecture workshop on new advances in mathematical and computational science. Today is Engineers Day, which is celebrated on September 15th as a mark of remembrance and tribute to Mokshagundam Vishweshwaraya birth anniversary. He got the government of India conferred Bharat Ratna onto him in 1955. He is a civil engineer, and we are very fortunate today we have our speaker who belongs to engineering background. That means he is working in engineering department, engineering college. Sir, I welcome you, sir.
Thank you, ma'am. So, should I start?
I welcome our today's speaker, Dr. Rizwan Sati, sir, for this workshop. Today, sir is going to deliver a lecture on mathematical modeling and simulation of nanofluid enclosed in a partially heated trapezoidal cavity, the finite element method approach. Now, I would like to introduce Dr. Rizwan Haq, sir. Sir presently is working as an associate professor in Department of Electrical Engineering, Bahria University, Islamabad, Pakistan. Sir got his PhD in Applied Mathematics in 2015 from Quaid-e-Azam University, Islamabad, Pakistan, and also he got his MPhil from the same university. His area of interest is in mathematical modeling, thermal management, structural designs, fluid dynamics, nanofluid, heat transfer, numerical analysis, boundary layer flow, cavity flow models, channel flow, peristaltic flow, homotopy analysis method, optimal homotopy analysis method, domain decomposition method, finite difference method, shooting technique, finite element method, and finite volume method. His total number of ISA impact factor publications is 127. Out of him, Q1 journals are 71 and Q2 are 33, Q3 are 19, and other categories are 4. SAR has completed 2 projects funded by Higher Education Commission Pakistan and Ministry of Higher Education Malaysia. His total impact factor is 248.37 and SAR got 9 awards, and he has 10 years of teaching and research experience, and 10 MS students were completed under the guidance of SAR, and 3 PhDs are under progress. SAR citation is 6878, and his H index is 46 and ITEL index is 106. SAR had so much international research experience. So with the J.M. Florian in Department of Mechanical and Material Engineering, Engineering Building, Western University, London, Canada, with Professor Dr. Zakir Homuch and Professor Dr. Taufis McCoy in Maula Ismail University, Irachidia, Morocco, and he visited Jilin University, Chang'an, and Peking University in China. 2 months research visit in Tiangong Mathematical Center in Northeast China in Jilin University, China. And this project was funded by Professor Dr. Ran Zhang, head of Tiangong Mathematical Center in Northeast China. And SAR has awarded so many, SAR got so many awards. So top 2% scientists in the world by Stanford University, together with the publishing house elsewhere and science tech strategies. Best researcher award of year 2019 from Bahria University, Pakistan. And again, best researcher award in the year 2018 from Bahria University, Pakistan. And excellent research award of the year 2017 from Bahria University. And productive scientist of Pakistan in the year 2017 under 40 years old. And the Research Productivity Award 2016 to 2017 under Pakistan Council for Science and Technology. Research Productivity Award from 2015 to 16 under Pakistan Council for Science and Technology. So award of TWA's Fellowship for Research and Advanced Training, and award of scholarship under International Research Support Innovative Program. Sir presented many papers in national and international conferences and also gave lectures and also be as a resource person for many national and international conferences, workshops. And I have a good association with Sir from past 3 years. We had some combined papers also. I thank Sir for accepting our invitation to be a resource person for this workshop. Thank you, sir. Thank you very much. Now I request Sir to start his lecture.
Thank you, madam, for such a detailed introduction. First of all, I would like to say sincere thanks to Dr. Sonitha for inviting me to a one-week virtual international lecture workshop on new advance in mathematical and computational sciences. So as madam already introduced myself, so now I would like to start my own presentation.
The volume, please, sir. Just you increase your volume, sir.
Okay, can you hear me now?
Yeah, now it's okay.
Okay, my hand free is quite far, so no, sorry. Okay, can you see the slides?
Yes, sir.
Okay, the title of my presentation is Mathematical Modeling and Simulation of Nanofluid Enclosed in a Partially Heated Trapezoidal Cavity via Finite Element Method. Well, first of all, these are some layout of my presentation. Initially, I would like to describe the fundamental concept of the fluid dynamics that consist of both Newtonian and non-Newtonian fluids. And apart from that, I would like to discuss some of the concept belongs to the nanofluid. And then I will like to introduce heat transfer of nanofluid and its application. And then I will go for the literature survey. In the very next slide, I would like to describe the mathematical method, that is finite element method. I will just give you the flavor. So if someone like to see the detail of that method, I can share my few of my articles. So then I will come to my own problem, that is geometry of the problem and its mathematical description and the physical phenomena. And then I will discuss the result and discussion of my own problem. And then in the second last slide, I would like to discuss some conclusion and some future direction for the current models. So if we talk about the fluid, fluid is actually the substance that deform continuously under the applied shear stress, no matter how small is that shear stress. Like we can see in this figures, like this smoke is also a fluid and this liquid is also a fluid. So we actually divide the fluid into the two parts. The one is the ideal fluid and the other is the real fluid. In the ideal fluid, the viscosity of the fluid is about to zero or approximately zero. The best example of the ideal fluid is like gases, air, smokes. So these are the examples of the ideal fluids. However, in the real fluids, the viscosity of the fluid is non-zero. The best example of the real fluids are like water, oil, and the paint, etc. So we do have a lot of example of the real fluids. So well, we can see in the in your daily life that there are a lot of example of the real fluids. Well, my study belongs to the real fluids. In the real fluid, as I have discussed, the viscosity is non-zero. So when we see the viscosity, this viscosity is actually deal with the fluid mechanics. This is the study of the fluid in motion by applying some forces, or in these forces can be the internal forces or external forces. This fluid mechanics is actually again divided into the two parts. The one is the fluid kinematics and the other is the fluid dynamics. In fluid kinematics, we actually discuss the fluid particle in the motion, the study of the fluid in the motion. However, in the fluid dynamics, the steady effects of the forces on the fluid motion, these are actually the external forces. This is known as the fluid dynamics. And this fluid dynamics is again divided into the two parts, that is fluid static and fluid kinetic. And fluid static is the study of the fluid that is on the rest. However, in the fluid kinetics, these are the fluid that consist of the relationship between the motion of matter and its causes, like how the fluid is moving and why the motion is created within the fluid. It is depending upon either the external force or the internal force. So here, this is the fundamental concept. This is known as the Newton law of viscosity. According to this law, the shear stress is actually proportional to the rate of deformation. This du by dy is actually the deformation, and this is tau. This tau is actually the stress. This stress is proportional to the rate of deformation, and when we remove the constant proportionality sign, this convert into the this convert into the kinematic viscosity and dynamic viscosity. And here the power n minus 1 shows the either over given fluid is the Newtonian fluid or the non-Newtonian fluid. If we substitute n is equal to 2, we have the Newtonian fluid. This relationship is linear when we substitute n is equal to 2. And when n is not equal to 2, this relationship is not linear. For the linear case, we have Newtonian fluid. And for n is not equal to, we have non-Newtonian fluids. Again, in the non-Newtonian fluid, we have different class of fluids. Here we can see this straight line, the red line, shows the Newtonian fluid, and this green, black, the purple, blue, and rest of the lines shows the non-Newtonian fluid. Again, we have various kind of fluids in the non-Newtonian, like the Bingham plastic fluids, like the pseudoplastic fluid and Dalton fluid. This is actually the rate of deformation. If the rate of deformation is linear, then we have Newtonian fluid, and if the rate of deformation is non-linear, then we have non-Newtonian fluid. So this all depend upon the Newton law of viscosity. Here, as I have discussed, the real fluid, when the viscosity is non-zero, this real fluid is actually divided into the two parts. One is the Newtonian fluid, and the other is the non-Newtonian fluid. In the Newtonian fluid, here we can see the mathematical expression. This is the linear relation, and this relation is non-linear. And when the relation is non-linear, then we have the non-Newtonian fluid. In the non-Newtonian fluid, the shear stress is not directly proportional to the shear rate. We again classify the non-Newtonian fluid into the three types. That is, number one is the time-dependent viscosity. The second one is the time-independent viscosity, and the third one is the viscoelastic fluid. In time-dependent viscosity is actually divided into the two parts. Number one is the rheopectic fluid, and the other is the thixotropic fluid. These viscosities are actually depending upon the time. Like in the rheopectic fluid, the apparent viscosity increases by duration of stress. Like custard, if you are preparing the custard at home in your kitchen, like if we keep moving the spoon within the custard, it will become thinner. And however, in the thixotropic fluid, the apparent viscosity decreases with the duration of stress, like corn flour. If you are drinking the soup at the home, like if you keep moving the spoon within the soup, corn flour soup, then it will become thicker. So this is the difference between the rheopectic fluid and the thixotropic fluid. Both are depending upon the time. Like we have force, like that force is known as time dependent viscosity. And the second one is time independent viscosity. Few of the fluids are not depending upon the time. These are known as the Dalton shear thinning fluids, pseudoplastic fluids, and the Bingham plastic fluids. In the Dalton fluids, we have cornstarch, sand, and water. In the pseudoplastic fluid, we have ice, blood, and hair. These are not depending upon the time. And similarly, we have Bingham plastic fluid. These are highly thick fluid, known as the toothpaste or the chocolate. They are very thick. and they are not depending upon the time. And the very last one is the viscoelastic fluid. Viscoelastic fluids are like the stretchable fluids, like the bubble is the best example. The bubble gum is the best example as the viscoelastic force. When we apply the force, it will become the stretch, and uh, when we release from any force, then it will come to the original position. Or the rubber band is another best example as of the viscoelastic fluids. So here, few of the fluid that depending upon the temperature, we can see the boiling cooking oil that is depending upon the temperature, and same with the falsic magma. In the boiling cooking oil, when we provide the heat, that is an external source, the high density molecules will switch from high density to low density, like lower surface to the upper surface, and same with the falsic magma. And similarly, when we talk about the density difference, the low density polyethylene is the best example to determine the fluid which are depending upon the density. And similarly, the fluid with the different densities, here we can see there are 3 or 4 different colors in this bar. These all the fluids have the different viscosity and different densities. That's why they are appearing with the different colors. And these are the example of the non-Newtonian fluids like emulsion, like engine oil, shear rate viscosity, like honey is the best example of shear rate honey, or the viscoelastic fluids. So these are the examples of the non-Newtonian fluids. Well, the nanofluids. Here I would like to discuss the idea of nanofluid. If we talk about the late 90s, to improve the thermal conductivity of the any working fluid like water, like ethylene glycol, they have very poor thermal conductivity. To improve the thermal conductivity of that fluid, they need highly cost pumping power. So in late 90s, in 1991, I guess, Chui have presented the concept of nanofluid. What he have done, he have actually substitute the small tiny particle within the base fluid, and these small tiny particles are known as nanofluid. Nanoparticles, and these nanoparticles are very small in size, approximately 1 to 100 nanometers in size. So well, we have like different kind of nanomaterials or nanoparticles. We can see in this slides that we have oxide ceramic, and the metal carbide, nitride, metal and non-metal graphites, and the carbon nanotubes. These all are the examples of the nanoparticles. And the base fluid, we have like water, ethylene glycol, and other coolant, oil, and other lubricant, biofluids, and polymer solution. These are the base fluid. When we when we consider any nanoparticle and the water, and we try to mix them up, then it will convert into the nanofluid. Here we can see we have a base fluid, and we have the nanoparticle. When we saturate these two things into a bar, and we have dispersion device. Okay, so when we put these nanoparticle within the base fluid, this will convert into the nanofluid. Well, nanofluid are actually two kind of mixture. One is the homogeneous mixture, and the other is the heterogeneous mixture. In the homogeneous mixture, the properties of the base fluid and the nanoparticle remain uniform. However, in the heterogeneous mixture, the properties of the base fluid and nanoparticle remain non-uniform, or their properties are not remain same. So this is the homogeneous mixture, and this is the heterogeneous mixture. And we can see in the figure 6, usually we have at number 1, 2, and 3, we have the different base fluid, engine oil, ethylene glycol, and water. And at 4, 5, 6, 7, 8, and 9, we have different kind of nanoparticle or particles. Okay, so we can see in this figure that the thermal conductivity of the nanoparticles or materials are comparatively high as compared to the base fluid. We can see in this figure. So these like 1, 2, 3, they have very poor thermal conductivity. However, these particles have very high thermal conductivity. Sorry. And in the very last case, the carbon is very efficient as compared to the particles. In among all these particles, carbon is highly reputable material that have very high thermal conductivity. So this carbon particle have very high thermal conductivity, maybe the 100 times more as compared to the other particle and the base fluids. Well, these are the some thermal conductivity of the various solid and liquids, like the nanomaterial liquid like water, ethylene, and engine oil. They have like 0.613, 0.253, and 0.145 thermal conductivity. However, this metal like sodium have 72 watt per meter Kelvin thermal conductivity. And similarly, this metal solid is copper and aluminum. They have like in 400 and 210. However, in the nanomaterials, nanometallic solids, they have very high thermal conductivity. We can see the single wall carbon nanotube, they have approximately 6600 watt per meter Kelvin thermal conductivity. And similarly, in the multiple wall carbon nanotube, we have like 3000 watt per meter Kelvin thermal conductivity. So we can see that the carbon nanotubes have comparatively high thermal conductivity to base fluid and solids. Well, only the saturation of particle within the base fluid is not sufficient. According to the study of Alina et al., she has presented that the particle shapes like blades have comparatively high thermal conductivity as compared to the other particle like platelets, slender bricks, and spheres. They have low thermal conductivity as compared to the plate. So if you consider the particles like blades, they give you high thermal conductivity. So shape of the particle also matter in order to improve the thermal conductivity. So this is one of the best example of the nanoparticle. Like usually the motion of the nanoparticle within the fluid is random. We can see this motion of the particle is random, and we can see these arrow signs. These are the random motion. And when we apply the magnetic field to these particle, then the motion of these particle will become uniform. We can see this figure number 8, that the particle are in the same direction by applying the magnetic field, and by removing the magnetic field, the motion of the particle is non-uniform. So here we can see, if in this figure, these blue shades are the cancer cells, and this red portion is called the of vessel of any human body part. So we can see that if we target these cancer cells by mean of nanoparticle, what we will do, we actually inject the medicine or nanoparticle or any drug within the blood. As I have discussed, the motion of the particle is random. What we will do, we will put the magnetic field at exactly at where the cancer cells are located. So as I have discussed, the motion of the particle are random, but when we put the magnet over there, all the particle will move toward these cancer cells, and they will continuously target these cancer cells, and gradually they will remove the cancer cells from this portion. So this is the best example of the application of the nanoparticle within the blood. Eh, Okay, these are the few examples of the few applications of the nanofluid, like the laptop and computer chips, microchannels, coolants, and anti-freezing system, sensors, medicines, viruses, and small molecules as well. So all of these are the examples, applications of the nanofluids. Heat transfer. Heat transfer is the fundamental requirement at any industrial level, where you need to remove the heat from one place to another place, or to transfer, or to add. So heat transfer is the fundamental requirement. And we have three major modes of the heat transfer. One is the convection, other is the conduction, and the number third is the radiation. In my problem, most of the cases I have discussed the convection. convection is actually the motion of molecules by colliding each other and transfer the heat from one place to another place by colliding the molecules. They are actually transfer the heat by mean of inertial forces, and these inertial forces consist of kinetic energy plus potential energy of the molecules. So these are the deficiencies of heat transfer in conventional fluids. Usually, as I have discussed previously, the base fluid, they have very poor thermal conductivity. So they are not workful unless you are not going to incorporate the nanoparticle. And same is the case with the thermal conductivity, same is the case with the heat transfer fluids such as water, ethylene glycol, acton, ethanol, and engine oil are known to have limited heat transfer capability due to low thermal conductivity. There is strong need to develop the advanced heat transfer fluid with the substantially high conductivity. So the overall comprehensive analysis of my study is to determine the deficiency in the heat transfer of the commonly used base fluid and then improve the thermal conductivity of that deficiency by incorporating the nanoparticles. So these are the best example of heat transfer and its application, like cooling electronics, automotive application, aviation, heat pipe modules, vapors, heat sinks, and some of the energy system and the healthcare system as well. These are some of the literature that belongs to my study. Initially, the concept of the nanofluid is actually presented by Chui in 1995. And then Ku and Ku presented the model for new thermal conductivity model for the nanofluid. And then Kulkarni et al. Present the natural convection heat transfer in the square heated from the bottom. And then JP Bangiorno present the very important article on the convective transport in nanofluid. In this article, he has discovered that the Brownian motion and the thermophoresis play an important role to improve the thermal conductivity. And then some of the references that belong to the natural convection in the square cavity and some of the experimental approach in the square cavity. And these are the few books that relate to the finite element method. Well, now I will move toward the methodology. What is finite element method? Finite element method is actually the numerical procedure to attain the approximate solution for the boundary value problem. It actually collect both differential equation, both the nonlinear system of differential equation and the boundary condition into the finite number of elements. And then these finite number of elements will convert into the linear system of equation that can easily solve by mean of the matrices that we have studied in the linear algebra. Why finite element method compared to the other numerical analytical approach? If we talk about the simple geometries, like this is the straight line, and this is a circle, rectangle, or cube, or cylinder, or eccentric cylinder. These all are the simple geometries. And these simple geometries can easily solve by any numerical approach like finite difference method or RK method. But if we talk about the complex geometries, like the motion of submarine within the sea or ocean, or the motion of aeroplane within the air, or the motion of blood cell within the vessel, or the random motion of the smoke, or the motion of piston within the engine. These are highly complex geometries, and the simple numerical method like finite difference method cannot determine the solution or construct the structure of this problem, because usually the finite difference method is applicable for the uniform grids. However, these structures are not uniform. They have like complex geometries. They have different corners, different shapes, different atmospheric effects on this shape. So these are highly complex geometries. For this, the people in the current era are going to use the finite element method or the finite volume method for such kind of complex geometries. Here we can see in the figure 12A to E, they have constructed some exactly the same kind of submarine according to the real picture. And similarly, the motion of aerodynamics within the air, they have constructed the same kind of structure by mean of finite element method in this picture, and they have created the same cell but what they are shown in this real picture. And similarly, the smoke and the shape of the uh, uh, engine block to in order to determine the heat loss within the engine. So all these are the complex geometries. These complex geometries are only solvable by finite element method or finite volume method. However, this complex geometry cannot be solved with a simple finite difference method. That's why finite element method is comparatively high efficient and more usable at the real time at the industrial level in order to get the results. Here are some drawbacks of other numerical method like finite difference method compared to the finite element method. As I have discussed, the finite element method can be used for the complex irregular shapes. However, this finite difference method is only for the simple shapes, as I have discussed in the previous slides. Finite element method is more accurate and high order. However, finite difference method is ordered based method that depend upon the step size, and there's a lot of stabilities issues if you increase the order. And finite element method is time taking simulation that depends upon the number of element, but this time taking simulation with high number of element will give you the more accurate result. However, finite difference method is fast to compute due to uniform grids. And finite element method is applicable for the solid mechanics, biomechanics, wave theory, phase change material, etc. But finite difference method is less accurate due to non-uniform nodes. And finite element method is mesh independency test is very important. By mean of mesh independence test, if like if we get the solution and if we further increase the mesh will not depending upon the solution after the testing of mesh independency. However, finite difference method is conditionally stable, or sometimes the results are unstable. So finite difference method is not that accurate to get the accurate solution. This is the procedure of the finite element method. Like if we have the unknown function u of xy to the boundary value problem, and this is the geometry of the problem. What we do, we actually divide this geometry into the number of elements, and we can see this geometry is divided into the number of elements and the nodes. Each square structure is known as elements, and each corner of the element, like this one element have four corners. These corners are known as nodes. So we can see that in this figure we are divided this rectangular shape into the 28 elements and 40 nodes. Then we will perform the calculation at each element. We will consider this element, only one element, and we will perform the calculation on each element. And then again, we will assemble all the element together again, like in this form, and we will get the solution of entire domain. And finally, we'll get the result for the current model in the form of the velocity. Like this is the mathematical procedure, the finite element method. Like uh, this this omega is the entire domain, and this gamma is the boundary of the problem. Let's suppose we are going to consider the Poisson equation with the boundary condition. We can see this is the Poisson equation with f is the unknown, u is the unknown function, and f is a source term with the boundary condition gamma. And let's suppose UE is the exact solution. This UE is the exact solution of the problem. And when we substitute this exact solution into the problem, we will get the accurate solution with no error, no residue. And in the finite element method, what we actually do, we suppose a solution U hat of xy. And when we are going to suppose that U hat is an approximate solution, and we will substitute this solution into the equation number 1, this solution will not satisfy the equation. Mean we will get some kind of error, like a minor error or maybe a little bit a major error. This error is known as the residual. Okay, so in finite element method, our main aim is to reduce this error. This error should be reduced and approximately approaches to 0 by considering U hat of x is a good approximation. For this, we can see that now the main objective is to find the approximate solution U hat of x such that R is close to 0. If the R hat is close to 0, then we are able to find the exact solution. So what we will do, we will introduce the weight residue function. This is the weight residue function. What we'll do, this weight residue can be multiplied with the original equation, this equation. Okay, and we will integrate for the entire domain, for this domain. Okay, so by multiplying this weight function to the original function, we will integrate by parts. When we integrate by parts, we will get the weak form of the solution. And when we get the weak form of the solution, we have different way to solve such kind of problem. Okay, in the finite element method, we have different way to solve such kind of problems. So here we can see this is the weak form of the solution, and we will perform the calculations. We will perform the calculation in the form of element. This is an element and this is the nodes. So here this is the weak form of the solution. We will consider only U of x, and we have different U. This is U1, U2, U3, U4, up to so on, U28. We have 28 U. We have 28 unknown function. We will consider only ui. Let's suppose this is ui, and ui is an unknown function that is depending upon the 4 nodes u1, u1 hat, u2 hat, u3 hat, and u4 hat. So we will multiply these all u1, u2, u3, u4 with the shape function. This n1, n2, n3, and n4 are the shape function, and this shape function is again added up and converted into the matrix form. And this matrix, this entire matrix for the entire system, is known as the stiffness matrix. And when we get the solution of this problem in the form of stiffness matrix, we are able to find the unknown function u. This k is a stiffness matrix, and this f is a source function. We are now able to calculate the unknown function u that is already defined in the previous slide. And finally, we'll get the solution. So we will calculate u1, u2, u3, u4, and then we'll add them up. This is divide and conquer rule. So this is the flavor of the finite element method. So let me summarize the method. Start with a boundary value problem, write the weight residue statement, obtain the weak form, use the interpolating equation for the element quantity that known as the shape function, assemble to obtain the global quantities, and like strong form to weak form and the Galerkin approach, and then we will convert into the matrix form. This is the entire formulation of the finite element method. So mesh independent sense for the Poisson equation. Why the mesh independency test is important? We can see in this square circle, we have approximately like 24 element in the green shade and 17 nodes. In this figure, we can see that when we consider the triangle with the 78 triangle and 55 nodes, our results are not smooth and not stable. But when we increase the number of triangles or number of element, that is 668, and the number of nodes are 380, our results are moving towards stability. And when we consider we further improve the triangle or elements, that is about 2648, and number of nodes are 1415, our results are more accurate as compared to the first two cases. And finally, in this case, we can see our results are very much accurate as compared to the all three cases. And now we are able to stop the mesh to get the accurate solution. If we further improve the mesh, the result will not affect, because we are already attained the accurate result or stable result for the current problem. So this is the entire procedure to test the mesh independency. This is my own problem for the current model. Let me check the time. Okay. Here we can see I have considered the trapezoidal cavity, and this is the heated portion. This is the adiabatic, like the rate of heat transfer is 0 in this yellow shade, and in the slant height we have considered cold walls, and this is the adiabatic position, and the entire position is also heated. And we further consider the base fluid as a water, and the nanoparticles in the form of Cu copper oxide. Okay, these are the assumption, like 2-dimension steady flow, incompressible flow, partially heated bottom surface with the slant heights are cold. Constant at the inner trapezoidal is cold, adiabatic, and heated. Like this shape have three cases, like heated, adiabatic, and heated. So we have three cases. These are the mathematical formulation for the boundary conditions. So at the left and the right side of the wall, the temperature is cold. T star is equal to Tc. That Tc denote the temperature of the walls are cold. At the bottom, we have three cases, like adiabatic, heated, and again adiabatic. For the adiabatic case, the rate of change of heat transfer is 0. The flux is 0. And for A, for less than A, and for greater than B. Okay, for both cases, the case is adiabatic, and in the middle case, this wall is heated, so T is equal to TH in the middle of bottom line. And in the top line, at the top wall, the case is adiabatic, and all the velocities at the surface of the trapezoidal cavity are 0. This means the velocities of the walls are 0. Okay, mean there is no source to move the fluid except the heat. So this problem naturally belongs to natural convection. And for the inner, we have TH. This is not only TH, this is T, the cold wall, and the adiabatic wall as well. So we have different assumption of the problem. Initially, we have considered law of conservation of mass. In order to check the inflow should be equal to the outflow, like the continuity equation, and then the conservation of momentum. This is the convective part. This is the convective part of the problem, and this is for the unsteady case, like the velocity of the fluid is unsteady. This is the gradient of the pressure, and this is the dynamic viscosity, like mu nf, and here del v is shown as like these all operators are already maybe I will show in the next slide. And this is the thermal expansion coefficient, like rho b nf, in order to determine the convection along the vertical direction. And this is the temperature difference that is multiplied with the gravitational force in order to check the convection, natural convection of the problem. And in law of conservation of energy, we have rho is the density of the nanofluid, Cp is the specific heat of the nanofluid, and the Knf is the thermal conductivity of the nanofluid. And this entire equation is known as the law of conservation of energy. Maybe all these operators are defined in the next slides. So here, delta is the nebula operation, V is the velocity field, T is the temperature, P is the pressure, F is the body force, del dot V is the conservation of mass, that is inflow should be equal to outflow, and the partial V over partial T is the acceleration term, that the change of velocity with respect to the time. For the study case, we are considering change in velocity with respect to time should be 0, and this is the advection term. Like in the previous slide, I have shown this slide. This is the advection term, and del P is the rate of pressure, and del dot del P is the viscosity, that constant control velocity diffusion term. This entire term is actually known as the diffusion term. This term is known as diffusion term. And then del dot Vt, that is advection term. Like this term is known as the advection, and last one is the net outflow of heat due to the conduction, and the very last term is shows the conduction, and the difference is different in temperature is known as a Beyonce driven term. Well, this is the entire mathematical model that is converted into the operator form, that's closed form to the into the expansion form. This is the continuity equation, this is the momentum equation, energy equation, momentum equation in the x direction, this is the momentum equation in the y direction. These are the velocities in x and y direction. And the last one is the energy equation, and where u and v are the velocities. These u and v are the velocities, T is the temperature, and mu nf is the dynamic viscosity, rho nf is the density of the nanofluid, and G is the gravity, and B is the thermal expansion coefficient, alpha is the thermal diffusivity, that is the ratio of the thermal conductivity and the specific heat. So all these expressions are defined over here. For this model, I have used the KKL model, where BNF is the function that is depending upon the base fluid of thermal expansion coefficient and the particle of the thermal expansion coefficient, and phi is the volume of nanoparticle volume fraction. If we put phi is equal to 0, we'll get only the base fluid, and alpha nf is the thermal conductivity, that's the ratio of the thermal conductivity to the density time specific heat, and rho nf is the density of the nanofluid. This expression is defined over here, that is again the sum of the particle and the base fluid, and if we remove the particle, phi will get only the base fluid, and this is the entire specific heat. This is the KKL model that is depending upon the K static and the K Brownian. Like we have both the motion of the thermal conductivity, the Brownian motion, and all the particles which are at static. So this is new kind of model for the effective thermal conductivity, and these all results are obtained from the experimental approach. These are the numerical values for the current model. These are the thermophysical properties of the copper oxide, and these are the thermophysical properties for the water. And after dimensionalize the problem, we'll get this form of the entire problem. Here, all the coefficients are defined after equation number 8, 9, and 10. And this pressure can be treated by the pseudo-constitutive relation. This pressure can be expressed in the form of law of conservation of mass. Like if we consider this delta, I just forget the name of this expression. If we consider this term is approximately very high, this will satisfy the continuity equation. So this pressure is depending upon this expression actually. Okay. And this is the non-dimensionalized form of the boundary condition. And okay, we have, I guess, shortage of time. Let me try to wind up my results. And this is the average Nusselt number for the entire model in order to determine the heat transfer rate at the surface. So I have considered the finite element method to solve this kind of trapezoidal cavity. I have considered different kind of mesh at the corner in order to get the best resolution at the surface of the or the border surface of the trapezoidal cavity at various corner of the problem. So this is the procedure to solve the problem, as I already discussed in the previous slides. And I have compared my result with the previous existing study. We can see these are my results, my theoretical results, and this is the experimental approach. And you can see that my results are quite close to the experimental approach done by the Procchini and Carvaro. So his results and my results are approximately same. So this is the best way to compare our result with the theoretical result with the experimental result. And this is the mesh independency test for the current model. We can see initially my result was fluctuating, but when I have increased the number of mesh, our results are going to stable with respect to the improvement of mesh. See in figure 50. Well, these are my result for the current model. Initially, I have considered the inner trapezoidal cavity as a cold, and in this case, the initial trapezoidal cavity as a adiabatic, and this trapezoidal, the inner trapezoidal cavity as a heated. We can see when we can consider the inner trapezoidal cavity as a cold, this heat transfer will not move away from this portion because this entire domain is cold. This domain is cold. This domain is cold. This domain is adiabatic. That's why this small trapezoidal cavity can resist the heat transfer rate from the middle of the portion. And here we can see this is not resisting. Here the fluid particles are going to disperse. In this case, the heat transfer is comparatively very fast. And this is the Nusselt number for the current problem, and this is the temperature profile for the vertical shape, and this is the velocity for the vertical shape. And we can see that from this portion to this portion, the heat transfer is gradually increases, and for the red portion, and for the cold portion, this is going to down. And for the adiabatic portion, this is going to disperse at this portion. So these are the three cases when the heat transfer is moving from bottom to top. Okay, and these are the three cases for when the inner trapezoidal cavity is cold, adiabatic, and heated. So same is the case for the velocity. We can see in the cold case, the velocity of the motion is very low. In the adiabatic case, the heat transfer is comparatively very high. And for the both bottom wall and the inner trapezoidal cavity is heated, the heat transfer is very fast away from this portion. These are the three cases when the inner trapezoidal cavity have three cases. And this is the case when this heated length is different. Here we can see this heated length is 0.2 unit. This heated length is 0.4 unit. This heated length is 0.7 unit. And this is entirely heated length. This length is fully heated. So these are the four cases for the heated length. Okay. In this case, we have maximum heat transfer as compared to these three cases. Okay, so this heat transfer is depending upon the bottom heated line. And these are the few results for the Nusselt number at the inner case. And these are the Nusselt number for the outer case. Like I have calculated the inner heat transfer for this case over here and this case over here. So heat transfer rate at the surface are calculated in figure A and figure C. In figure B, I have calculated the heat transfer at the vertical position, like in this way, So, okay, so from bottom to top, we can see initially the heat transfer rate is decreases from starting from 1 and it improving at this position, and then again from hot to normal position, because at at near the surface heat transfer is maximum. We can see at this position heat transfer is maximum, at this position heat transfer is maximum, at this position heat transfer is maximum, but at this position heat transfer is minimum, at this position heat transfer is minimum. So we can see at this position heat transfer is maximum, that is 1, and this portion we have low, then maximum, then 1, like maximum, and then low. So these are good compatible result with these geometries. And this is the variation of Rayleigh number for the various cases. We can see that when we increase the Rayleigh number, it is highly impact and influential to heat transfer rate. By improving the Rayleigh number, the convection is very strong. Like we can see, when we consider 10 raised to power 5.7, the heat transfer is comparatively very high. So we can further increase the Rayleigh number, but our results are going to stop over here. That's why I have considered the maximum value of Rayleigh number is 10 raised to power 5.7. And these are again the Nusselt number at the outer domain, at this domain. And this is the Nusselt number for the inner domain. These are the 4 portions for the Nusselt number. And this is the velocity at the vertical mean position. Sorry, temperature at the vertical mean position. I have draw over here, and this is the velocity profile for the vertical position over here. And again, in this slide, I have considered the nanoparticle volume fraction. Phi is equal to 0, phi is equal to 0.1, phi is equal to 0.2. So I have considered these 3 cases for the nanoparticle volume fraction. And again, I have computed the Nusselt number at outer position, at the inner position, for the vertical temperature and vertical velocity. So these are the results. And these are the results when the inner trapezoidal cavity is small and the aspect ratio is 0.75, 1, 1.5, and 2. When we increase the aspect ratio of inner trapezoidal cavity, we have different kind of result for the velocities along the u direction and the v direction, and same with the streamlines and the isotherms. So we have very interesting result if we enlarge the size of the inner trapezoidal cavity. Here we have different theoretical model for the effective thermal conductivity. This is the Maxwell model, defined equation number 15. This is the Hamilton-Crossan model, defined equation number 16. And this is the Zui model, defined equation number 17. And according to this model, we have different output result for effective thermal conductivity. We can see when we consider Zui model, we have high thermal conductivity for single wall carbon nanotube with the water. And for Hamilton-Crossan model, we have low thermal conductivity. In Maxwell model, we have very low thermal conductivity. So this Maxwell model gave you the low thermal conductivity, and this Zui model gave you the high thermal conductivity. And we can see that the percentage increase in the thermal conductivity when the phi is 0.02, this Zui model gave the 27.2% increase as compared to these two. And when we consider the phi is equal to 0.1, we get this 132% increase as compared to the Hamilton-Crossan model and the Maxwell model. So Zui model is quite efficient as compared to the other 2 models. These are the concluding remarks of the problems for my study. And these are some of my latest research that is going to held in my coming days. This is the lid-driven model for triangle cavities when the upper surface are moving with the different velocities. And we can see that and this is the time-dependent problem. It's more important, these are time-dependent problem. And when we will give the velocity of the top valve with a different direction, here the fluid motion will come into the form of circulation. And this is the blood motion within the arteries. We can see then there is no cholesterol level within the arteries, then the blood flow is quite uniform. And when there is some kind of cholesterol level within the arteries, then what kind of nature of the blood flow within the arteries, and if it is further increase the obstacle, like if a very high level of cholesterol within the arteries, then the blood flow motion is quite slow, and this will cause the heart attack for the human being. Okay, so I'm going to discuss such kind of model with the finite element method, and this is one of my problem, that is going to discuss the heat loss within the engine. If there is some kind of leakage with the engine block, then what kind of heat loss within the engine block by mean of finite element method. So these kind of problem I'm going to handle in my future work. Thanks for your attention. Any question, please?
Thank you so much, sir. Sir, am I audible?
Sure.
Yeah, it's audible, madam. Continue, madam.
Thank you so much, sir, for your nice elaborating discussing about the mathematical molding and simulation of nanofluid enclosed in a partial heated trapezoidal cavity finite element approach. Really very nice session, sir. You are starting with the basics of fluid, real fluids, and finite element method, and what is your research in your subject. You are explained very neatly. No doubt our researchers and our mathematicians all are happy to listen, and they definitely benefit you of your talk. Thank you so much, sir. Thank you so much for your patience explanation all these once again.
Yeah,
and
actually-
also thank you so much for your accepting our invitation within by phone and within a week. Thank you. Really, our Department of Mathematics is proud to say, luckily we get research person. Once again, I thanks to all participants also. Any queries, you please ask, ma. Sir, having a very patience.
Thank you, ma'am.
Anybody wants to ask any question? Sir, I have one small doubt, sir.
Sure,
Sir,
sure,
you please
ma'am.
go
No.
through your figure number 29, sir, 29. You said your research paper, sir, 29, figure number 29, sir. The engine in graph, sir, figure 29, sir.
Okay, ma'am. Let me. Actually, there are a lot of figures, so it is quite difficult
Yeah,
to
yes,
move.
yes, sir, yes, sir. 29, sir, 29.
I'm sorry. Yeah, this one.
Sir, sir, what is the engine Blackboard model? Why the engine Blackboard model having the hole, sir?
Usually, if you see the piston of the engine, the top layer of the engine, we can see there is motion of the piston within the engine block. Okay,
Yes.
and if there is some kind of leakage, we are able to determine like how we can determine the leakage of the seals from the engine block. So this is the best way to determine the heat loss if there is some kind of leakage within the engine block. So these kind of holes are actually appearing in the real time. Like we can see, this is the engine block, and here this is the motion of the piston, and we will see if there is any kind of leakage from the sides, from the circle, and from the nut bolt or anywhere else. We can determine the heat loss from that engine block. It is not from only from the hole.
Thank you, sir. Thank you.
Sure,
Thank
ma'am.
you, sir.
Okay, sir. Thank you. Thank you very much, sir.
Thank you, ma'am. Thank you.
Thank you, sir.
Okay.
And I wish all our participants have enjoyed your lecture. It's very
Yep.
interesting.
Thank you, ma'am.
It is just lively. You have shown with figures and all graphs and all those things in
Actually,
three-dimension and very colorful. It is very colorful, I have to say.
Actually, this is the best way to attract the audience, but unfortunately, most of the people from the mathematics are not from the engineering background. That's
Yes,
why
sir.
sometimes it is quite difficult to understand these things in the form of engineering. So that's why I have just compatible both mathematics and engineering. So it is helpful for those who are working in applied mathematics.
Yes.
So
Yeah.
if someone like to collaborate with me, I'm most welcome to all of you from the India. Actually, in mid of 2016, I have two students from the India. They were like doing the research with me, and they already completed their PhD. So
Okay, sir.
it is
Okay,
very good.
thank you very much, sir. You have invited us for collaborating work with us.
My
So
pleasure.
sure, sir, we'll use that opportunity.
Sure, ma'am. Sure. My pleasure. My
Sure,
pleasure.
sir.
Thank you.
But sir, actually, we are not from engineering background, sir. My,
Uh,
so I'm
yeah,
from mathematics background itself. But
I
luckily, today is Engineers Day in India. We are celebrating Engineers Day. So on that occasion, you engineer, you have came as a resource person.
it's my pleasure.
So it is very lucky, sir.
It's my pleasure to be part of you. Thank you, ma'am.
Yes, sir. Yes, sir.
Take
Thank you, sir. Thank you once again, sir.
Thank
And
you. Take care.
I wish all have a nice day, and we will meet tomorrow at 2:30 p.m.
Okay, ma'am.
Thank
Thank
you
you. Take care.
once again for all the
Bye.
participants and for today's resource person, Rizwana Ullah, sir.
Thank you, ma'am.
Okay. Thank you, sir.
Bye.
So you can stop your screen sharing, sir. So one small request, our participants are asking about the PPT, sir.
Sure, ma'am. I can share with you.
Okay, sir. You share with me, sir. Then I can share
Okay.
to them.
Okay. No.
Okay.
No
Okay.
problem.
So you can close your screen sharing, sir.
Okay, ma'am. I will try to. Like this is my first time to use this software.
Cisco,
It's quite
yeah,
difficult.
yeah.
In our university also, we are using Microsoft Teams, sir.
We are actually using the Zoom and the Microsoft Team. That's why I'm not familiar with the software. So never
Okay,
mind.
okay, sir. Yes. మేడం క్లోజ్ చేస్తున్నారా
నాది కూడా కావడం లేదు మేడం, ఏదో ప్రాబ్లం ఉంది. చూస్తున్నాను నేను కూడా, చాలాసేపు అయింది ట్రై చేస్తున్నా, పోవట్లేదు. క్లోజ్ చేసేయండి మేడం, మీరు చేయండి. బాయ్ మేడం, బాయ్.
ఓకే బాయ్ చెప్తా ఇక్కడ క్యాంపస్ ఫీడ్బ్యాక్ ఎట్లా తిరుగుతున్నాం Hello, Deepa. Hello, Dr. G. Deepa. Hello. Hello, Dr. G. Deepa.
Yes, ma'am. Yes, ma'am.
So you have been as a host here. Can you please wind up the session?
Yeah. Okay, ma'am. Thank you.
Okay.